In this video series, we will discuss E1 reactions. This video series builds on the ideas we covered in the previous series on SN2, SN1, and E2 reactions. If you find that these videos move too slowly, you can use the answer document as a supplement or replacement for the video explanations. Now, let's take a look at this first problem. Please pause the video and try this problem. And now let's discuss the solution to the problem together. Let's start by numbering all the carbons. Next, let's identify the roles that atoms will play in the mechanism. We can identify the neutral bromine as a good leaving group. You should have memorized that neutral chlorine, neutral bromine, and neutral iodide are good leaving groups. Next, we identify carbon 2 as our alpha carbon, because carbon 2 is the carbon attached to the leaving group. We see that carbon 2 is a secondary alpha carbon, because carbon 2 is attached to two other carbon chains, carbon 1 and carbon 3. Next, we look for an atom to play the role of nucleophile or base. Now, nucleophiles and bases are both electron donors. So the best clue for a nucleophile or a base would be a negative formal charge. But we don't see any negative formal charges in our starting materials. So instead, we're going to identify the neutral oxygen in the water as a nucleophile or a base. Because of its lone pair, a neutral oxygen can play the role of nucleophile or base. The lone pair on the neutral oxygen makes it want to donate electrons. Well, which will it be? Will the neutral oxygen play the role of nucleophile or base? Well, the problem told us that we need to draw an elimination mechanism. SN2 and SN1 are substitution reactions. The S stands for substitution. SN2 and SN1 use nucleophiles. E2 and E1 are elimination mechanisms. The E stands for elimination. E2 and E1 use bases. The problem tells us we're using an elimination mechanism. That means that this mechanism will be E1 or E2, and that means we're going to use a base, not a nucleophile, in the reaction. So now we predict that the neutral oxygen in the water will act as a base. Now the problem tells us that the mechanism will be an elimination mechanism, so we know the mechanism will be E2 or E1. But which is it? Will the mechanism be E2 or E1? The way to decide is to use a table. We can use this table to determine the mechanism. I've discussed extensively how to use this table in my earlier video series. Now we have a secondary alpha carbon, which puts us in the middle row of the table. Middle row of the table for a secondary alpha carbon. The atom we're going to use as our base is the neutral oxygen. We'll use the neutral oxygen in the water as our base. And notice that the table actually reminds us here that water, the neutral oxygen in water, is a weak base. So I'll update what I wrote down here. I'll write WB to remind myself that this neutral oxygen is a weak base. Well, now the table predicts that the major mechanism here will be SN1, and the minor mechanism will be E1. So which mechanism should we draw for this problem? Well, remember the problem said draw the elimination mechanism. So that clue, the problem told us to draw the elimination mechanism, that clue tells us that in this case we should draw the E1 mechanism, even though it's the minor mechanism. Remember that the E in E1 and E2 stands for elimination. Always write down the name of the mechanism. So we'll write down that we're using an E1 mechanism here. So we used this table together with the clue in the problem to determine that the mechanism here will be E1. Notice that the most important factor in organic chemistry is formal charges. There's a huge difference between a neutral oxygen, which puts us in the left column of the table, and a negative oxygen, which puts us in the right column of the table. So make sure you're aware of the formal charge on the atom that you're looking at. This is an oxygen with a neutral formal charge. I discussed how to identify formal charges in the starting materials in much more detail in the SN2 video series. So you can see this is a very important table. You can find this table in a handout, and there's a link to this handout in the video description box. You should click that link and print out this table to use while you're going through this video series. Notice that on this same handout, there's also a summary of what happens in SN2, SN1, E2, and E1 mechanisms. This is a very important summary. So now we want to focus on what happens in an E1 mechanism. There are two steps in an E1 mechanism. Notice that this number one might be misleading. Even though E1 has the number 1 in its name, that doesn't mean it's a one-step mechanism. E1 is a two-step mechanism. In a later video in this series, I might explain why E1 has the number 1 in its name, but it doesn't stand for the number of steps. There are two steps in an E1 mechanism. In the first step, the leaving group leaves the alpha carbon. So let's draw the electron pushing arrow to show the leaving group leaving the alpha carbon. The definition of a leaving group is that a leaving group receives electrons to leave an atom. Notice how this arrow is consistent with that definition. We're showing the bromine receiving electrons to leave the alpha carbon. Now we draw the product of this step. Any electron pushing arrow tells you to erase a bond, or to draw a bond, or both. And I think it should be intuitive that this electron pushing arrow tells us to erase the bond between carbon 2 and the bromine. I've erased the bond between carbon 2 and the bromine. So we applied this rule. We're breaking this bond because the tail of the arrow is on the bond between carbon 2 and the bromine. Now, carbon 2 is losing electrons at the beginning of this arrow, so we have to change the charge on carbon 2. Carbon 2 started neutral and it lost electrons from the arrow, so carbon 2 should become one step less negative. That means carbon 2 becomes one step more positive. That means carbon 2 ends up with a positive formal charge. That's this rule. Make the atom that loses electrons at the start of the chain of arrows, or at the start of the single arrow, one step less negative, which means one step more positive. Then at the end of the arrow, the bromine is gaining electrons. The bromine started neutral and gained electrons, so the bromine becomes one step more negative and ends up with a negative formal charge. Always make the atom that gains electrons at the end of the chain of arrows, or at the end of the single arrow, one step more negative. The most common mistake students would make on this step is forgetting to change the formal charge at the beginning of the arrow. The most common mistake students would make on this step is forgetting to change the formal charge on carbon 2 from neutral to positive, but it's crucial to get that formal charge correct. Be careful to continue to number all the carbons, and make sure that you number the carbons in the product consistently with the way that you numbered the starting material. Is the mechanism finished, or do we need another step? Well, we should expect we need another step because we've only completed one step, and we know that E1 is a two-step mechanism. But another clue that the mechanism is not finished is that so far our main product still has a formal charge. The reaction is usually not finished until the main product has no formal charge. Well, here's what happens in the second step for E1. Base takes the beta hydrogen and pi bond forms between alpha and beta carbons. So you can see that at this point it's useful to continue to label the alpha carbon, and we should also now start to label the beta carbon. I'm going to continue to label this carbon as the alpha carbon because it meets this definition. It's the carbon with a positive formal charge. So in this context, it's helpful to define the alpha carbon as the carbon attached to the leaving group, as here, or the carbon with a positive formal charge, as here. Then the beta carbon is defined as a carbon attached to the alpha carbon. So in this case, we have two beta carbons. Carbon 1 and carbon 3 are beta carbons because they're both attached to our alpha carbon. By the way, I forgot to mention, a good name for this molecule at this point is carbocation intermediate. It's called a carbocation because it has a carbon with a positive formal charge. Carbo refers to carbon. Cation refers to a positive ion. A carbocation is a carbon with a positive formal charge. And this is called an intermediate because it's generated in the middle of the mechanism. This intermediate is the product of the first step and will form the starting material for the second step. That's what an intermediate is. So E1 mechanisms create a carbocation intermediate. That's an important term. So let's go back to the alpha and the beta carbons. Notice that in E1 step 2, the base takes the beta hydrogen. So in order to draw the arrow for that, I have to draw in a hydrogen on the beta carbon. Here's the electron pushing arrow that shows the base taking the beta hydrogen. Remember that a base is an electron donor, so it goes at the beginning of the electron pushing arrow. Now we need another arrow for that same step, another electron pushing arrow to show the pi bond forming between the alpha and the beta carbons. Well, notice that when the base takes this hydrogen, that's going to free up the electrons in this bond. Hydrogen can only have one bond at a time, so if the hydrogen is forming a new bond to the water, it's going to have to lose the electrons in this bond. And what are we going to do with the electrons in this bond? Well, we can use those electrons to make this pi bond that we need to form between the alpha and the beta carbons. And the way we draw that, we draw an arrow like this to show that we're going to use the electrons that are freed up from this covalent bond to make a pi bond between the alpha and the beta carbons. Notice that it would be wrong to draw the arrow like this. The arrow should not point directly to the alpha carbon because that's not the correct arrow for showing pi bond formation. If the arrow was pointing directly at carbon 2, that would not show a pi bond. The correct way to show that you're forming a pi bond is to put the head of the arrow in the bond region between the two atoms that you're forming the pi bond between. So now we've shown one arrow to show the base donating electrons in order to take the beta hydrogen, and a second arrow to show the pi bond forming between the alpha and the beta carbons. The most important tool for getting the correct electron pushing arrows is the formal charges. So let's make sure these arrows are consistent with this formal charge. Notice here that carbon 2 is at the end of the series of arrows. That means that the positive charge is going to be gaining electrons. Well, that makes good sense. Things with a positive charge want to gain electrons. Notice that carbon 2 is going to be gaining electrons from the new pi bond, even though the arrowhead is not pointing directly at carbon 2. So these electron pushing arrows are consistent with these formal charges. A base donates electrons to take a proton from an acid. So this base goes at the beginning of the electron pushing arrow to show that it's donating electrons to take this proton. Therefore, we're treating, or I guess it's convenient to say that this beta carbon is the acidic atom. I'm going to call this beta carbon the acidic atom because this is the one that's donating the proton. I've labeled carbon 3 Sa for strong acid. In a carbocation intermediate, it turns out that the beta carbon is strongly acidic. This positive formal charge makes this molecule very eager to lose a proton so that the molecule can gain electrons and get back to neutral. In organic chemistry, we usually don't get an acid-base step between a weak acid and a weak base. In organic chemistry, either the acid or the base usually has to be strong in order for an acid-base step to occur. This positive formal charge makes this molecule strongly acidic. So we can get an acid-base step even though water is only a weak base. Now we need to draw the products of this step based on the electron pushing arrows. Well, does this electron pushing arrow tell us to erase a bond, draw a bond, or both? I hope it's intuitive that this arrow tells us to draw a new bond between the oxygen and the hydrogen. So I'm going to draw the H2O turns into H3O to show that the oxygen has formed a new covalent bond to a new hydrogen. We use this rule to see that we're forming a new sigma bond. We form a sigma bond when the arrow head is pointing to an atom which was not already sharing the electrons at the tail of the arrow. I know that's a little bit complicated, but this arrowhead is pointing to this hydrogen. Notice that in this picture, the hydrogen is not yet sharing the electrons at the tail of the arrow. The electrons are starting in a lone pair on the oxygen. In this picture, the hydrogen is not yet sharing those electrons. I know that's a little bit of a complicated rule, but with practice, it becomes fairly intuitive to see that this arrow tells us to form a new sigma bond. Now, this oxygen is losing electrons at the beginning of the chain of arrows. Therefore, this oxygen should become one step less negative, which means the oxygen becomes one step more positive, which means the oxygen ends up with a positive formal charge. Make the atom that loses electrons at the beginning of the chain of arrows one step less negative, which means one step more positive. The most common mistake on this step would be forgetting to change the formal charge at the beginning of the chain of arrows. The most common mistake would be forgetting to change the charge in this oxygen from neutral to positive. Now we move on to this arrow and go through the same process. Does this arrow tell us to break a bond, form a bond, or both? Well, I think it's clear that this arrow tells us to break the bond between carbon-3 and the hydrogen and to form a new pi bond between carbon-2 and carbon-3. The tail of this arrow is on the bond between carbon-3 and the hydrogen. So that arrow tells us to break the bond between carbon-3 and the hydrogen. The head of this arrow is on the bond between carbon-2 and carbon-3. That's the kind of arrowhead that tells us to form a pi bond. So we used these two rules to break this bond and to form this pi bond between carbons 2 and 3. I already basically broke this bond when I moved the hydrogen from this position to this position. Now, carbon-2 is gaining electrons at the end of the series of arrows. So carbon-2 becomes one step more negative, one step less positive. Carbon-2 started positive and gained electrons, so carbon-2 ends up neutral. Make the atom that gains electrons at the end of the chain of arrows one step more negative, one step less positive. Notice that even though this arrowhead isn't pointing directly to carbon-2, carbon-2 is still gaining the electrons from this arrowhead when carbon-2 gains this new pi bond. I'm really taking my time and talking through the logic of how to interpret these electron-pushing arrows because it's important for you to learn these rules for using electron-pushing arrows to draw the products of a mechanism step, but obviously you need to practice interpreting the electron-pushing arrows until you can draw the products much more quickly than the time it takes me to talk through these steps. Is this the final product, or do we need another step? Well, we can guess that maybe we're done because we've completed the two main steps that we expect from an E1 mechanism. And we can confirm that we're probably done by using this rule. The reaction is usually finished when the main product has no formal charge. Well, this is what I would consider the main product of this reaction, and you can see that it has no formal charge. So that's a strong clue that we're finished with this mechanism. Notice that it's not possible to get rid of all the formal charges. We couldn't get rid of the formal charge on this oxygen or the formal charge on this bromine. But the reaction is usually finished when the main product has no formal charge. We would consider this the main product, and it has no formal charge here. Now that we've finished this E1 mechanism, let's try to summarize how would we describe the starting materials and the product from this E1 mechanism. Do you know what type of functional group would we say that this molecule contains? This molecule is called an alkyl halide. Alkyl refers to carbon chain, and halide refers to the bromine here. Bromine is considered a halogen because it's from the 7th column of the periodic table. Chlorine and iodide are other common halogens that you might see in alkyl halides, a carbon chain attached to a halogen. Do you know what type of functional group have we produced in this product? Here's the answer. This product is called an alkene. An alkene is a molecule that contains a carbon-carbon double bond. E1 and E2 reactions produce alkenes. E1 and E2 reactions produce alkenes. You should memorize that. And you also need to memorize that a good starting material for an E1 or an E2 mechanism is an alkyl halide. And you should know that the intermediate for a E1 mechanism, intermediate for an E1 mechanism, is a carbocation intermediate. That does not apply to an E2 mechanism. Notice that this is a table for determining the mechanism for alkyl halides. Now, let's clear up a couple of details that you might have been wondering about as we went through this mechanism. Were you wondering, why did we use carbon-3 as the beta carbon rather than carbon-1? Well, the reason is that it doesn't matter which of these beta carbons you use, because they're both going to produce the same product. You can see that because carbon-1 and carbon-3 both have the same connectivity. They're both going to result in the same E1 product. You describe the connectivity of a particular atom in a molecule by describing the complete series of all the atoms that the atom is connected to and all the atoms that those atoms are connected to, etc., for the entire length of the molecule. For example, to describe the connectivity of carbon-3, we would say that carbon-3 is connected to 3 hydrogens and to a positive carbon. And the positive carbon is attached to 1 hydrogen and a methyl group. Now, if we were going to describe the connectivity of carbon-1, it would be the same description, wouldn't it? Carbon-1 is connected to 3 hydrogens and a positive carbon. And the positive carbon is attached to 1 hydrogen and a methyl group. So we can see that carbon-1 and carbon-3 have identical connectivities. So since carbon-1 and carbon-3 have the same connectivity, it should be apparent that they will result in the same E1 product. If we did use carbon-1 as our beta carbon, we would get this product. And I hope it's apparent that this molecule is just the same molecule as this one. They're just rotated different ways. If you rotated this molecule around this vertical axis, you could easily rotate this picture to look like this picture. So that shows that carbon-1 and carbon-3 do result in the same E1 product. So you can use either carbon-3 as the beta carbon or carbon-1, but you should not use both because professors will usually take off credit if you include redundant products. If you said that this was the product and that this was the product, you would probably lose credit. Don't leave redundant products in your final answer. Here are some guidelines that are useful for drawing an E1 mechanism. You should always label the alpha carbon and the beta carbon that you will use in the mechanism. Since it turned out that we didn't use this beta carbon in the mechanism, maybe we should now erase that beta symbol, but label the alpha and beta carbons you're using in the mechanism. It should be obvious that only a beta carbon that's attached to 1 or more hydrogens can be used for E1, because the beta carbon has to lose a hydrogen. And we saw that if 2 beta carbons have the same connectivity, they result in the same E1 product. These are all guidelines that would also apply to an E2 mechanism. For completeness, I will mention that this connectivity rule does have an exception. If the E1 product has 1 or more stereocenters, then it's possible that 2 beta carbons with the same connectivity might result in different E1 products. We can see that this E1 product does not have any stereo centers, so we can see the exception doesn't apply for this problem. This exception is not tested very frequently in most introductory OChem courses, unless perhaps you're taking a particularly challenging course. Now, another detail that might have worried you while we were going through the mechanism is, in the second step, why did we use the water as the base instead of using the Br- as the base? After all, this bromine has a negative formal charge. Doesn't that make it want to donate electrons? Well, it turns out that Cl-, Br-, and I- are very weak bases. As a result, when water or alcohol is the solvent, we usually prefer to use the water or alcohol as the base, rather than Cl-, Br-, or I-. Well, in this case, we had a water solvent, so we preferred to use that as the base, rather than the Br-. Notice that anytime water or alcohol is included in the starting materials, we generally assume that that's also the solvent for the reaction. Why are Cl-, Br-, and I- such weak bases? Well, maybe you know that HCl, HBr, and HI are very strong acids. And Cl-, Br-, and I- are the conjugates of those very strong acids. And you should know that the conjugate of a very strong acid is a very weak base. The upshot is that when water or alcohol is present, we generally prefer to use water or alcohol as the base rather than Cl-, Br-, or I-, despite the fact that the water and alcohol are neutral, and these species have negative formal charges. Another detail, notice that this problem involves heat, and that it's fairly common for E1 and SN1 mechanisms to involve heat, but notice that the heat didn't play any significant role in our solution to the problem. All right, so we've completed our first example of an E1 mechanism. Now would be a good time to pause the video and memorize what happens in the two steps for an E1 mechanism. I hope you actually paused the video and memorized what happens in these two steps. When you have this memorized, you're ready to proceed to the next video in this series and try more practice with E1 mechanisms. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.